All right, good morning, welcome all. Here are some relations from matrix calculus. Who would like me to discuss this in the plenum? 1, 2, 3, 4, 5, 6, 7. Okay, quite a few hands. Okay, then we do this briefly. Okay, I'm giving you the pragmatic point of view, and then, okay, no, let me start the other way around. I start with explanation, and then we go to the pragmatic point of view, okay? So, X is a vector, and if the numerator is a scalar, and we differentiate it with respect to a vector, the result will be a vector. Fine. If the numerator is a vector and the denominator is a scalar, then we will also get a vector, also fine. But if we differentiate one vector with respect to another, yeah, so this is a vector and this is a vector, we will get out a matrix. And now we need to decide how do we want to lay out these things. And there are two consistent choices. There is the numerator layout and the denominator layout. And both are equally fine. And some scripts, books mix the two, which is perhaps a bit unfortunate, but facilitates notation. I usually stick with this one, numerator layout. So what do I mean by this? So if we focus on this case here, if we have dAx by dx, this is a vector and this is a vector. And now I want to give a different dimension, so I'll use a different one here. I will call this one z. So they can have different dimensionalities. Now both, in my notation, usually vectors are column vectors. Yes, so I have a derivative of one column vector with respect to another column vector. And now I need to decide how do I want to lay out the contents. And in numerator layout, the numerator, I'm going to say here, the numerator wins. So what I mean by that is that I'm going to keep this column vector in its usual shape. So I will write z1 up to zk. But down here, I will write dx1 up to xl. And now, well, we get out a matrix, and up in the top left corner, I get dz1 by dx1. Next to it, the numerator has 1, so this stays a column vector. So I get dz1 by dx2, and we continue until dz1 by dxl. And here we have dz1, oh, excuse me, this is now dzk by dx1. Here we have dzk by dxl. Okay, so this is the convention used in numerator layout, and in denominator layout, it's just a transpose of this. Now, if you substitute z with, for example, this thing here, I don't want to do it now step by step, but then you will see that the result is A transpose. And can I argue this quickly? This is a scalar. This in the numerator layout became a row vector, so we get out a row vector. But you can also do it coefficient by coefficient and check. And well, the reason I tend to work with numerator layout is that normally if we have in ordinary calculus, if we have something times x and I differentiate with respect to x, then I'm left with something. Yeah? And this is what I like here, that if I differentiate this with respect to x, I just get the something which was in front. Yeah? Here I have something times x, I differentiate with respect to x, and I'm left with something. However, if I now have this formula, then I must transpose, and the ordinary rules, chain rule and product rule and so on apply. So if I have this kind of expression, when we were deriving PCA or linear regression, I just wrote 2 times x transpose times A, but this was assuming that A is a symmetric matrix. And if A is not a symmetric matrix, then, well, if I differentiate with respect to x, we apply the normal, I think it's called product rule of differentiation. Yeah? So I get x transpose A, this is here. And then I differentiate x transpose with respect to x. I need to get this transposed, which is here. And now you see that once I have x transpose A, and the other time I have x transpose A transpose. So this is the result. And if it's symmetric, then of course this is just 2 times A. So this is the detailed explanation. I would say the pragmatic point of view would be that these enumerator layout you should know by heart, and then the rest, like this one, is just application of these rules. Okay, so and of course one can do everything component-wise, and that is also fine. But when working with vectors and matrices, this usually makes for faster manipulations. Okay, any more comments, questions? Yeah? Yeah, chain rule also works. So we have the, and this then brings us to Jacobians, and we will need that in backpropagation a lot. Yeah, but yes, chain rule applies. And in notably when we do this with neural networks, it's going to become more complicated, because then we have not just vectors and matrices, but tensors, and then derivatives of some tensors with respect to other tensors. And this becomes less easy to write in this kind of notation here. But for vectors and matrices, it's just fine. Okay, very good. Then by my count, today is the 8th lecture. So we are going, by the end of today, it's already almost a third of the semester gone. So it's really time we approach neural networks which have steamrollered, in most domains or in most application domains, they have won over competing methods. And I want to, by the end of today, arrive at the loss function that is typically used when training neural networks for classification. Yeah? So the cross-entropy loss, and today we will see where it comes from. And a warning, there will be, so the literature, the field of machine learning has given 2 bad names, or 2 wrong names. And well, the first one is not really the fault of machine learning, but it's the fault of statistics, because they call this logistic regression. And let me immediately put the regression in quotation marks, and for good measure, let me strike it through, because it should really be called logistic classification. So the title is misleading already, yeah? So it is a classification method, and it is, in fact, it belongs to this class of discriminative classifiers. So we look at the left-hand side of Bayes' theorem, and we directly try and estimate the posterior probability of one class given our features without modeling the class densities themselves. And this is a discriminative classifier which is linear in the log odds. And what the log odds are, we will see in a moment. Okay, but before we go there, a brief reminder of what we did in linear regression, or at least what was the maximum likelihood view or perspective of linear regression. We were in linear regression assuming that we have some feature x, we have some response y, and then we have observations. And we were assuming the following. We were assuming that conditioning on any single feature x, like if I condition here, conditioning on x, I get a normal distribution. Yeah? So the distribution of my observations around the mean was supposed to be Gaussian, normally distributed. I also get a Gaussian here, and I also get a Gaussian there. And in this homoscedastic formulation, we assume that the variances of these Gaussians are all the same, and that the mean is a linear function of our features. So we would write this as a normal distribution with a mean which is given by x transpose beta and a variance of sigma squared. Okay, short side note, this straight line here is not going through the origin, and yet when I write x transpose beta, it sounds like it should go through the origin. Because if I set x to 0, well, 0 times beta is 0, so it sounds like it should go through the origin. And this is shorthand notation. What I'm normally using are these homogeneous coordinates. And in homogeneous coordinates, we take some original features, like maybe the original features in this particular case would be x1 tilde. And I'm constructing a new feature by taking as the first feature, as the last feature, just a constant 1. And then I define that this is my new coordinate vector x. And if I now write x transpose beta like here, then beta has several components. It has one component for each of my linear features, and it has one component for the 1, which is the intercept. So this would be the homogeneous coordinates. Which I'm using most of the time. And I'm doing it so that I don't need to write an equations like this one, x transpose beta plus intercept. It's integrated here by having an extra dimension, which is constant 1, and having an extra parameter in this vector here, the intercept. Okay, so this was the ML view of linear regression, all fine. But now let's look at a classification scenario. I'm trying to make a very similar plot. highlight the similarities. And we now have a class 0 and we have a class 1. And normally when I made these plots about classification, I always showed some feature space. So let's say I took a 2D feature space and then I made pretty plots and I said the circles are the one class and the crosses are the other class, okay? Now today I'm using a slightly different representation. Here in this picture, we have just a one-dimensional feature space. And today, well, I could use the circles and crosses if I wanted, yeah? But really it's coded by where I put those observations. Yeah? So let's say I have observations belonging to this class here, and I have observations belonging to the other class there. Okay, and these observations are invented just like the ones that I invented up there. Situations like this arise in practice, yeah? That let's say we have maybe the luminosity and we want to classify is it a supernova or not, and we have not just the luminosity but we have some other source of information, and then for higher luminosities it tends to be supernova but not always, and vice versa. We have other objects which are not supernova but sometimes can be very bright. Yeah, but so generally speaking, as we increase this feature, we tend to have greater probability of having class 1, and for low values of the feature we tend to have class 0. All right, now I could go and do linear regression. You know, I could apply this model here and I would obtain something like, maybe like so. I'm doing this very faintly so I can erase it. So in regression, we would ignore the fact that these are circles and that these are crosses. We would just pretend that these are points on the plane, just like above, and we would fit it with a straight line. And maybe I got the slope a bit wrong, you know, maybe it should be a bit steeper, but something like that. Huh? All right. And then we could say, all right, let's use this. And in the early days of pattern recognition, people tried it. Yeah, they said, okay, you know, we have invented linear regression, works great. Let's just use it for classification. And then we can still, you know, say we put a decision threshold here in the middle between class 0 and class 1. And so we get a decision boundary, which is right here. So we get a classifier predicting that on the right-hand side here, we have the class 1, and on the left-hand side, we have the class 0. And it's not terrible, right? I mean, this classifier here, I mean, we could do worse. Yeah, it's sort of okay. But can you think of any, you know, problems? Where would this, how could this go wrong? Think of, yeah. Yeah, that is always true, yeah. Also, you know, here we have no guarantee that the dependence is linear. You know, also this line that I, so, you know, there's always the question of, you know, linear or not, yeah. So let's pretend that linear is enough. Yeah? That's the same assumption we made up there. We're willing to walk with it. If you think of, yeah, it's very sensitive to outliers. In what sense? Very good. So we have this observation here, the outlier. And we think now, what does this outlier do to my linear regression? As we know, in linear regression, we have like a quadratic force acting between the observations and the line. So if I now build a linear regression model taking into account this outlier, I will get something which is extremely shallow, a very, not a steep slope, but a very low slope. And notably, my decision boundary will shift to the right. Yeah, so this observation here, this outlier, it was not in contradiction to our classifier. Yeah, we have a supernova, and it was amazingly bright. So this should not change our decision boundary, but it does. Yeah. If I now take a lower slope here, and I look where this lower slope intersects my decision threshold, this lower slope will move the decision threshold to the right. And then suddenly, these perfectly fine supernovae are no longer classified as supernova. Yeah, so you're right. Okay, so if we did linear regression here, this would be very sensitive to outliers. And well, this is because we are fundamentally using the wrong statistical model. Yeah, we are using normal distribution. And indeed, when I condition on the straight line, I get a nice normal distribution. Or another way of saying this is, if I look along this straight line here at the distribution of points around my straight line, so I put an, let's say I put an eye here, and the eye looks along this direction, the eye sees a nice Gaussian distribution around the straight line. Okay, I'm cheating a little bit because the eye looks at an, in regression, we are looking at the vertical distance, not at the orthogonal shortest distance, but you forgive me, all right? But here, I have points down here and points up there, and there's nothing normal about it. This doesn't look like Gaussian at all. So the question is, what does it look like? And let's do this again. In particular, in the middle here. So I'm again conditioning here, and I'm conditioning here, and I am conditioning there. And I'm asking, what is the distribution at these various points? Now, normal distribution doesn't cut it, because I always have either this outcome or that outcome. And the distribution which models this kind of thing, either one outcome or the other outcome, that's the distribution that we also use to describe coin tosses. Yeah, we throw a single coin and we get either head or whatever the other thing is called. Tail? I don't know. All right. So I could, for example, do a histogram. Yeah, I could count how many points are in the vicinity here. And I'm now doing, just like I plotted a Gaussian, I'm now showing a bar plot where I say, okay, I have a few observations from this class, and I also have a few observations from the other class. So this is meant to be a histogram rotated. Yeah? Here, I only have observations from this class and 0 from the other class. Here I have lots of observations from this class and pretty much zero observations from the other class. Yeah, so I have these histograms with just 2 bins. And this distribution describing coin tosses is also called the Bernoulli distribution. Bernoulli, or statisticians abbreviated as Ber. And Ber has a single parameter, namely the probability of success. Yeah? So the probability that the class is 1, and this single parameter of the Bernoulli distribution is called mu. And all right, but here the feature does not enter. Yeah. So what we need is we somehow need to make this depend on the observation we have. Sorry, you can write a second line, but I'm going to use the sponge and say I want to have the probability of class 1 at some feature x. And this is given by a parameter mu, which will also depend on x. Okay, so just like I wrote normal distribution here, I'm now writing Ber, and the normal had two parameters. It had its location and its variance, and the Bernoulli is a distribution with a single parameter. It only has this chance of success. The variance can be computed from it. Yeah, so the the expectation of a Bernoulli distribution with parameter mu is just mu, and the variance you can compute easily. Okay, so, but now the question is this mu of x, how do we, what functional form do we choose? So I write mu of x, this is great. We want something that's somehow linear in x, but this mu, it's the probability. Yeah? So it can be, it must not take values below 0, and it must not take values above 1. And so what one does is in logistic regression is to use an ansatz where we say that the distribution or the observations y are distributed according to a Bernoulli distribution, and now this mu of x is assumed to be a sigmoid of something which is linear in the features. And so here we want something. I need another color. I need more complementary colors, really. So this is supposed to be yellow here. We want something which is close to 0 in this particular example here on the left-hand side. It should be close to 1 on the right-hand side, and in between it should somehow, we could do something like 0, linear 0, but we are going to use something a bit smoother. We're going to use some kind of this type of function here is a sigmoid, and we're going to use some kind of sigmoid. And now in principle, now the question is which sigmoid are we using? And depending on your prior beliefs, the sigmoid that we're using here is either a reasonable choice or it's like, the only possible choice. So people who like to think or who like to model nature in terms of a family of distributions called the exponential family, they think there's a compelling reason to use a particular kind of sigmoid, namely the logistic sigmoid. Just curious, the exponential family, have you encountered this somewhere in statistics? Yes. 1, 2. Can I see really high hands? Okay. Could you tell me in what content you came across it? Okay. Okay. And did you do it with Ulrich Schwarz or with Tristan Barrault? Schwarz? Okay. And what members of the exponential family did you see at the time? Okay. Yeah. So surprisingly many turn out to be members of that family. Yeah, so including the Bernoulli, including the normal, and then well, the binomial, the multinomial, and I'm trying to remember if Poisson, but it's a big family of important distributions. Okay, and if you want to know all about it and more than you want to know, there is a fantastic textbook about the exponential family. So exponential family by Jordan and Wayne Wright. This is Michael Jordan. Usually when you, I mean, depending on your Google bubble, the first Michael Jordan you find is either the basketball player or this one. So the one is a true hero of basketball and the other hero is a true hero of Bayesian machine learning. Yeah, amazing guy. By the way, the reference that I'm going to offer for today's lecture is a 1995 paper from Michael Jordan called Why the Logit in Logistic Regression or something like that. Okay, good. So the logistic sigmoid, and it is defined as follows. Like so. And we can now multiply with e to the plus beta transpose x and we get this equivalent form here. And this is the functional form we now assume for mu. And again, this is the probability that we observe class 1 at some location x. Okay, and now this expression here, we can also solve for beta transpose x. And then we get ln mu over 1 minus mu. So it's the ln of the probability of y equals 1 given x divided by the probability that y equals 0 given given x. And this here is called the odds. Even non-machine learners and statistics know this term. In the UK in particular, betting is a bit sport, you know, betting on soccer matches, on outcomes of elections and so on. And when you go to a bookmaker, there's always, you know, people talk about what are the odds of, you know, this prime minister lasting more than that many weeks and so on. So this would be the odds. And this thing here would be the log odds. And the log odds here are now, for us, linear in B transpose X. And these log odds, they have units. And you know, in physics, normally we need to specify what are the units of a quantity. And it looks dimensionless because we divide a probability by a probability, but still, because it's such an important property, it is endowed with a unit which is called the logistic unit. And this is abbreviated as a logit. And people use, you know, many, this has been reinvented over and over, so many different terms are used, but certainly logit is one of them. Okay. So far, so good. So we have picked a particular kind of sigmoid. We have a probabilistic model. Now, the only thing left to do is estimate the parameters in our model. And the fitting of the parameters, or machine learners would talk about the training of the parameters, is using maximum likelihood. Okay. And then we can ask, what's the likelihood of making these observations here that we have? What's the likelihood of these observations given some parameter? And I'm going to write now the likelihood of beta, even though on the right-hand side, the beta is not going to show up immediately. So we have a product of the probabilities of our individual observations. This product goes over all observations, over all the n observations that we have. And now, using this convention that our classes are 0 and 1, then okay, what do we have here? So if the true class label is 0, then we have something to the power of 0, and this is just going to be 1. And then we're going to be left with this term here. So if the true class label was 0, then we are left with the probability of y equals 0 given this particular location x. So this is fine. And vice versa, if the true class label is 1, then this is going to be, the exponent is going to be 0. This entire thing is going to be 1. And then we are left with here the probability of class 1 given x. So the curly braces here, they refer only to the term, you know, excluding the exponent. All right, so this looks reasonable, I think, I hope. And instead of the likelihood, it is often more convenient to work with the negative log likelihood. and the negative is often left implicit. So if people say log likelihood, they usually mean negative log likelihood, but they don't even say the negative because it's too many syllables. And so this, so I wrote here beta, and the beta enters implicitly because for the mu, we are using the formula that you see on the top of the board here. And so we can write a negative log likelihood L of beta, and taking the logarithm, this will turn the product into a sum. And then we have the negative, so there's a minus, and then we have yi log mu of xi minus 1 minus yi the log of 1 minus mu of xi. And this thing, depending on what lectures you have followed already, you have implemented this already. This is in fact the logistic loss, or the log loss, or the cross-entropy loss. If you remember entropy, entropy was the summation of minus p, ln p. And here we don't have the same distribution, but here we have the indicator for the true class. And here we have our estimated posterior probability. And so it's the cross-entropy between these two distributions. This is where the name comes from, yeah, the cross-entropy loss. Or because we have two classes here, this is the binary cross-entropy loss. And this is the thing that's actually used to train neural networks for classification. Good. I think I've exhausted you enough for this hour. So after the break, we will take this to multiple classes and study a few properties. But I'm happy that starting from, you know, a wrong model, we have now come to a procedure to find the parameters, namely by minimizing this thing here, which is the binary cross-entropy loss that's used for logistic regression, but also used in neural networks. And we have a 15-minute break.